So, dear students, till the internet connection is not stable, I will use these videos to upload my content, and um, so everything will be same. Just all the platforms are same. Um, so I will share the Jamboard slide link and the videos in the classroom. So till now we have done till Coulomb's law. So what is a Coulomb law? Same. Coulomb law defines the force between two charges. So let us assume two charge. So this is Q1 and this is Q2. So they are placed at some position with respect to origin. So let us say this is at position R1 and this is at R2. So by Coulomb's law, if we want to determine the force on charge Q2 due to charge Q1, so what will be the force on Q2 due to Q1? So this will be proportional to the magnitude of Q1, magnitude of Q2 divided by 4 pi epsilon, the permittivity, and the square inversely proportional to the square of distance between Q1 and Q2. So this is I denoted this as to be R12. So this is your R12, vector R12. It starts from 1 and ends at 2. And the force, whatever the force is experienced by Q2 due to Q1, the direction of that force will be in the direction of this distance vector R12. So we can take a unit vector in this direction. Okay, so this is Coulomb's law. This is the magnitude, and this is the R12, unit vector R12 is the direction. So let us write this R12. So vector R12 can be written as final position vector minus initial position vector. So the final position vector is R2 and initial position vector is R1. Okay, so this is final position vector. This is initial position vector. Okay, so if you want to determine the unit vector R, sorry, so if you want to calculate unit vector R12, so what it will be? It will be vector R12 divided by the mod of vector r1. This is an important concept. So here we can say it is 1, 2. So this is an important concept, and we have done this in Coulomb's law. So let us use this concept, force concept, to determine build the concept of electrical field intensity. Electric field intensity, which you also called as electric field. So electric field intensity. So what is electric field? So these fields are just defined by the forces itself. Just how we define a force, on what quantity, because there should be two charges to define force. So let us take a source charge. Source charge is whose field we need to determine. Let's say this is the position at which we need to define the field of this charge q1. Okay, so now we will determine just a force that is being experienced by a test charge. What is this? A test charge. The force experienced by this test charge due to this q1. So we know that what we have to do, we have to just see that what is the distance vector, and just the force will be in the direction of this distance vector. Okay, so if you want to write the force equation, then what will be the force? So force, let us say this is source, then P is the position, so force SP will be q1 q2 qt upon 4 pi epsilon the direction of unit vector RSP. So now we define another quantity, which is electric field. Electric field at point P. So electric field at point P will be force per unit test charge. Okay, so this will be q1 upon 4 pi epsilon RSP whole square into in the direction of RSP. Okay, So now you can see the electric field at point P only depends upon the source charge, and it is inversely proportional to the distance um, from the source to the point at which we are trying to find the electric field. Okay, so electric fields are line of forces. So wherever you want to find the electric field, you need to place a test charge there. Okay, so the force is the most experienced thing in electrostatics. All the other things are derivative of your force quantity. So electric field is one of them. It is derived from force. Okay, now let us study some group of charges. What is the effect of uh, how the some group of charges can be um, can be analyzed. So whenever more than one charge is present, so let us say there is a charge q1 and there is a charge q2. Okay, and we want to find the electric field at a point P. Yeah. Okay, so I want that what is the total electric field at point P. So it is very simple. You just need to find the electric field at point P due to charge q1, and then find the electric field due to charge q2 at point P, and thus then just add them vectorly. So if this is your E1, you field E1, this is R1P, and you can easily write these line vectors, distance vector, R2P is the distance between charge Q2 and P. So the electric field due to Q1 will be in the direction of R1P. So this we can write it as electric field due to 1 on P, okay, and this electric field due to Q2 in the direction of R2P. So we can write it as to be E2. So the final electric field at point P will be E1 plus E2. Okay, and now this is very simple. So this should be a vector quantity. So sorry for that. All these quantities are vector quantities. So in your syllabus means there are three basic charges, charge of distribution that you need to understand. The first one is line charges. The second is surface charges, and the third is volume charge. These are charge distributions. Line charges means the charge will be distributed on a line throughout. Surface charge means the charges will be distributed on a plane, on a surface. And third, the charges will be distributed in space, in 3D. So all these will be denoted by their charge density. So you can define rho L here. Rho L is the total charge on a single line divided by the line length. Okay, so in differential form, this could be written as dq divided by dl, where you can take dl as to be tending to 0. Okay, similarly you can write for the surface charge density. So your surface charge density will be rho s is equal to dq upon ds, limit is ds tending to 0. Okay, and the volume charge density you can similarly write as to be rho v with dq divided by dv, limit dv tend to 0. So these are three charge densities which we will analyze. So first of all we will see the line charge density. So let us determine electric field intensity due to a line charge. Electric field intensity due to line charge. Okay, so we will determine a line charge. We define a line charge as to be placed on the z-axis. Okay, so let us say this is your z-axis, this is your y-axis, and this is your x-axis. Okay, now we need to find the electric field intensity due to this line charge at this point P. Okay, so we need to calculate the electric field at this point P. So what we will do, we know that these charges are distributed on this line which is placed on z-axis. Now we need to take these small charges, and we need to calculate the electric field at this P point. And then what we will do, we will add all the effect due to all the charges on P point, like we did in previous case. We calculated the electric field due to individual charges and then added up. So similarly we have to do here as well. So here what we do, we take a small dl quantity. So a small dl length will be taken. Okay, and due to this dl length there will be some charge on this. Let us say dq. Dq is the charge present in this dl length. So we will determine the electric field due to this charge on this point P. So we say this as to be R1P, the distance vector between this charge and this test point P. So we know the electric field will be in the direction of this distance vector. So let us say this as to be E1P. Okay, so we can write E1P here. This stylus is a bit slow, so pardon for that. So when we write E1P, so what it will be? It will be the charge itself, will depend upon the charge itself, dq divided by 4 pi epsilon R1P whole square. It will be inversely proportional to the distance between this charge and P and in the direction of R1P. Okay, so here we can write our R1P. So what will be R1P? So vector R1P will be some final position vector of P. This is RP, the position vector of point P, minus R1. The R1 is the position vector of this dq charge. So here we can mention this, show the distance vectors. So this is your vector R1 and this is your vector RP. Okay, so to determine vector RP you need to define these positions. So P point can be taken as in cylindrical coordinate system. In cylindrical coordinate system, this will be P will be first of all the radial distance. So let us say the radial distance is rho. Then the angular distance from the x-axis, so it is 90 degree here, and the z-axis distance, so it is on xy plane, so z will be 0. Okay, similarly the position vector position of this dq length is on the z-axis, so your rho is going to be 0 and your angle you can take it as to be 90 degree. And if you remember in our last class, when the class was interrupted, I took this angle as to be 0 degree, uh, but if you will see, by taking 90 degree as well, the point remains on the same axis, um, axis uh, and location. Just the angle of view is different here. So it doesn't matter, it is the angle is 0 or 90 degree. Previously we took 0 degree, and that brought some complexity in the equation. So here we are taking 90 degree to remove that complexity. And on the z axis it is placed at some length, let us say z. Okay, so now we can write the this vector r1p. So you can easily write rp. So what will be rp? So rp will be rho a rho minus 90 degree, sorry, plus 90 degree a5 plus 0. Okay, and what will be r1? So minus, what is r1? R1 is 0 on row, so it will be 0 plus, so here as well it is 90 degree, so we can take 90 degree a5 and plus z az. Okay, so r1p will become what? Rho a rho 5 will be cancel out, minus z a z. Okay, so now we will complete the equation of E1p. So our electric field, due to our small charge, so it will be small electric field because it is due to small charge. So this will be dq. So dq you can write rho l into dl, no? The charge density into the length. Okay, now 4 pi epsilon and the mod of r1p. So mod of r1p, so it will be mod of this r1p, it will be rho square plus z square under root. So it will be rho square plus z square under root, and we have to take whole square. The electric field is inversely proportional to the square of the distance, so under root will be cancelled out, so it will be 2 by 2 under root and square of that. So and what will be a unit vector? So you can always write unit vector rho a rho minus z az is your vector divided by the mod of the vector. So what is the mod of the vector? What is the mod of the vector? Mod of the vector is rho square plus z square. So it will turn out to be rho l dl rho a rho minus z az divided by 4 pi epsilon rho square plus z square 3 by 2. Okay, now this is the electric field due to discharge. Okay, now if we take a charge that is equidistant from the origin but in the negative z direction. Okay, so now what will be the electric field at this P point, because we need to consider the whole line charge, so we are taking just the negative of that. Okay, so here electric field will be P to P, very simple. Now, so this is your electric field P R, that is placed at R to P distance, and the length is dl itself. Okay, so let us see what is E to P. So if we write our E to P, you know it, so what it will be, same, the length is same, so the charge will also be same, and it is positive throughout. The charge density is positive. By epsilon. Now the distance will also remain same because that is equidistance from the origin, so we will take it rho square plus z square 2 by 2. Now your unit vector will change. Now it is R to P, and if we see here, now just observe this thing. When we took R1P, it was RP minus R1. Here R1 is positive, it is positive Z, but when we will consider this DL, it is placed at minus Z. Okay, this is placed at Z, this is placed as minus Z. P is not changing, so your final position vector will remain same, just the initial position vector will change. It will contain here minus sign. So what will happen, R2P will consist this positive, same this, but this has to be positive. So similarly same thing we can incorporate in our equation. So it will be, so R2P, unit vector R2P, so we can write it rho a rho plus z a z divided by the same under root rho square plus z square. Now let us add these two things. DE1P plus DE2P. You can see very easily E1P consists minus z quantity minus z az, and E2P consists of plus z az. So az quantity will be eliminated. So what will remain, remaining thing will be rho L dl rho a rho divided by 4 pi epsilon rho square plus z square 3 by 2, and this will be 2 times. Okay, this will be 2 times. So now what we need to do, we just need to integrate this electric field from minus infinity to plus infinity, because we our line charge is an infinite line charge. So what if we will do, so this will be the effect we have to take. We need to integrate uh, integrate our electric field from minus infinity to infinity. Like I need to put the summation here. Let me put the summation. So all electric field that is present so here this is due to positive line charge, due to positive z, and this is due to negative charge z. So what is the effect? It is twice. Okay, so now if we need to integrate this thing from minus infinity to infinity, just see here, from minus infinity to infinity. So what we need to do, because these are symmetrical, this line is symmetrical to um, this xy plane. So what we can do, we can integrate from 0 to infinity and make it twice. Now it is coming, we are adding this we are adding the electric field due to the positive charge, and due to this this positive z and this negative z. So the concept is that you need to just add this positive z and make it twice. So it will incorporate the effect of this negative z axis. Okay, so what we need to do, we need to just calculate the electric field due to E1p, dE1p. We need to just integrate this thing. We need to integrate dE1p and make it twice. So d1p we can write so d1p is rho l dl rho a rho divided by 4 pi epsilon rho square plus z square 3 by 2. So just integrate this thing from 0 to infinity. Okay, and the electric field due to EP, what it will be? It will be just twice of this. It will be twice of the electric field due to just the positive z. Okay, same thing you are doing here in this thing. What you did, you calculated dE1p. dE1p is this thing, and you multiplied 2 with it to take the effect of dE2p. Okay, now just you have to integrate. This is a simple integration, uh, but you have to do some manipulations to do this integration. So here your dl here your dl will be equal to dz. Why so? Because you are considering dl on the z-axis only. So any length you consider, that will be equivalent to dz. So converting dl to dz and considering z to be rho cot theta, consider z to be rho cot theta, and now just differentiate this. So your dz will be cot theta, differentiation of cot theta is cos square theta, so minus rho cosec square theta d theta. Okay, so you can write rho square plus z square the quantity that is in numerator of the electric field. So it will be rho square 1 plus cot square theta. This will be rho square cosec square theta. Now replace all the quantities in the integral itself. So what it will become? So your E, now I am terming it as E at P, because we have considered all the charges from minus infinity to infinity, and this will become minus 2 comes from the because there is symmetry around the xy plane, so it will be rho L rho square cosec square theta d theta divided by 4 pi epsilon and rho cube cosec cube theta. And mind you, you also need to convert the this angle as well. These limits will be converted because you are now taking d theta. So how you will do it? So take z is equal to rho cot theta. So your theta will be z by rho cot inverse. So if you put your for z is equal to 0, theta will be equal to pi by 2. Okay, and for z equal to infinity, your theta is going to be 0. So theta will be cot inverse infinity, that will be 0, and theta for z is equal to 0 will be theta will be cot inverse 0, and where cot is 0, it is at pi by 2. So we can change this limit. So your now E will become minus 2 pi by 2 to 0 rho L sin theta. One cosec theta will be remaining in the numerator, others will be cancelled out, so it will become sin theta at the numerator. So it is 4 pi epsilon rho. So integrating this, it will be 2 cos theta. Sin theta, integration of sin theta is minus cos theta. So it will be cos theta rho L divided by 4 pi epsilon rho, and put the limit as to be pi by 2 and 0. So you can easily say this. When you put 0, cos theta cos 0 is 1, so it will give you electric field has to be 2 rho L upon 4 pi epsilon rho minus, so minus is what, and the lower limit, that will be pi by 2. So cos pi by 2 is 0, so minus it will be 0. And from the starting itself, we know that only a rho component is remaining, this a rho component. So this electric field at P point is only having a rho component. That is what in cylindrical coordinate, that is radial component. Yeah, okay. So here as well it will be a rho. This is the magnitude. So electric field we can write as to be 2 rho L upon, sorry, we can cancel this 2 term from the numerator. We can bring it to denominator, 4 pi epsilon rho, and it will be in the direction of a rho. So this is the electric field due to line charge at point P. And the thing to observe is that this electric field is only depending upon the radial distance of the point from the line charge. Okay, and this is directed in the radial direction only. So if you consider a line charge like this, so what will be the electric field? And mind you, this is an infinite line charge, so the electric field will be, that will be always in radial direction. Okay, considering this has to be z axis, this has to be y axis, and this has to be x axis. So this will be around like in a circle. If you turn this, if you join the locus of this of the tip of all these electric field, this will come out to be a circle that is coplanar with xy axis. So xy axis, it is so this circle lies on this xy axis, so it will be just radially outward. The electric fields will be coming from this line charge radially outwards. Okay, so this is our electric field due to electric field intensity due to the line charge. So now what you can do, you can just not consider this this line charge to be infinite. You can limit this line charge to a practical number, means the line charge will be of L length, and now you can again calculate the electric field due to that finite line charge on that P point. So this is an assignment for you, that you need to calculate the electric field due to a finite line charge, a line charge which is having a length L. And same thing you need to do, you need to calculate the electric field at a point P on y axis. So this is your assignment, and in the next class we will solve the we will try to find the electric field due to surface charge density. Okay, we will take infinite surface charge infinite surface charge plane, and we will try to evaluate the electric field at a point uh, given. Okay, so thanks for now. So the next slides will be shared in coming 1 to 2 days. So thank you for that being there. Thank you.